Okay, let's begin the class. So this week, it would be me to deliver this lecture about decision tree classifier and naive-based classifier and key nearest neighbor algorithm. So last week, I think we have already talked a little bit about classification. Just in case you cannot remember. So let me use another example different from which Professor Wang gave you last week. Think of you attend this course, okay, and finally you will take the final exam. Now you are here. You're trying to train your brain. You're trying to learn something. And when you attend the final exam, you won't say the exactly same questions as you have seen during the lectures. That's why you cannot just memorize. You need to understand. That is also what classifier does. So in today's lecture, we will use this example for most of the classifiers. And as you can see, so these are the attributes. And this is what we are going to predict. Forgive my terrible handwriting. Okay. And for the prediction, we first consider just the two different classes, yes or no. And for each attribute, we first consider all the attributes, assume all the attributes are discrete. Okay, that's why for age, we don't have 30 or 31, 32, but we categorize, discretized them into three categories, like smaller or equals to 30, between 31 and 40, and larger than 40. Okay, so for a decision tree, what you will finally see is a tree structure. And for a tree structure, we need to know what does a node represent, what does an edge represent. And for node, I think most of you should know that a node can be categorized into external node and internal node. So in a decision tree, an internal node corresponds to a single attribute. Like in the previous, let me see if you can see this. Yeah. For example, a single node can be age, or can be income, or can be if he or she is a student, can be his or her credit rating. Okay, and the external node, which is the leaf, corresponds to a decision, or a prediction, or a class label. In this case, it is a yes or no, represents whether he would buy or he would not buy a computer. And each age corresponds to a value or a value range of the attribute. We will first introduce the ID3 algorithm and use this algorithm as an example to help you understand the whole picture. And then we will talk a little bit more about another algorithm to show you the difference. And for such a decision tree, what we have is at the root, we look at the age. And according to different values of the age, we decide which children or which subtree are we are we going to? For example, if the age is smaller or equals to 30, then we will go here to see whether he or she is a student. And notice previously this large table are splitted according to different values of age are splitted into some subtables. Okay, so what decision tree can give us is it actually represents the knowledge as rules, and very simple rules, which are if-then rules. And such rules are easier for human beings to understand. And one rule is corresponding to a path from the root to a leaf. For example, this path tells us that if the age is between 31 and 40, then by computer equals to yes. And this path means if the age is larger than 40, and notice that you use and to connect different clauses. So and credit rating is excellent, then by computer equals to no. Then we wonder, how do we construct such a decision tree? The key observation from the previous examples, such as this one, I think what we can observe is that firstly, the samples or the data, like this or this, the samples are getting fewer after we split. And the second observation is each node can be viewed as a root of a subtree. For example, when you go here, then you can view this part as a subtree corresponds to this part of data, which means the big problem can be split into sub-problems, but have similar forms. This gives us the intuition that it seems that we can do a recursive algorithm to construct the tree. So for a recursive algorithm, firstly we need to decide which direction shall we go. Shall we go top to bottom, or bottom to up, or bottom to top? And apparently for decision tree, we go from top to bottom. And another thing in a recursive algorithm is that we need to decide two things. One is how do we split or partition the data or problem. The other is when shall we stop. So we will leave how to partition the problem to the next slides, but let's first focus on when to stop. So in decision tree, as you can image, there are three stopping conditions. One is that there are no samples left. So basically, you have no data. Then you do not need to split. because you have nothing to split. The other is all samples have the same label. Then you do not need to split because you have already reached your conclusion. The third one is that you cannot split or partition. That is because, for example, in this example, you first partition the data according to age. Then in this sub problem or subtree, you cannot split the data according to age again because all the ages are the same. And since the number of attributes is limited, so you cannot, so once the age is used, actually in this subproblem, you will see no age. Or you pretend you cannot see age because then you will only have 3 attributes for you to choose in order to partition the problem. Then you can imagine that in this specific example, the height of the tree or the depth of the tree would be no longer than 4. Okay, then we'll look back to the overview. So at start, all the training examples are at the root, and each time you partition the samples, or partition the data, recursively based on a selected test attributes. We will talk about this later, how to select the attribute. And then you decide whether you should stop or whether you should recursively do the same procedure again. So far, so good? Okay. So for ID3, the criteria of selecting the attribute to partition is called information gain. The information gain is actually the difference of expected entropy before and after the split. So let Pi be the probability that an arbitrary tuple or sample in D that belongs to Ci. So we can get the estimation of this probability Pi, which should be the number of tuples that belongs to this class divided by the total number of data. Okay, so the expected information, which is actually the entropy, and I think we have mentioned that last week. So the entropy needed, the entropy of D is calculated by this formula. Okay. And the information or the expected entropy after the split, after splitting D into V partitions is the sum. Sorry, it's the sum of, this is the portion of the data belongs to a specific class, belongs to a specific partition. And this is the entropy of the data belongs to this partition. So you can see this is the expectation because for each partition you get its entropy and get its portion, and you do the sum. So what you have here is actually the expectation of the entropy after you do the splitting. Then the information gain is the difference between these two. And it is easy to prove, which I won't do it here, but it's actually easy for you to prove it as well. This information gain will never be negative. So intuitively, you will always get a smaller entropy after you do the partition. Then, if we look back here, yeah, here is fine. Although no one has asked, but do you ever wonder why do you split age? You split it into 3 partitions, but not 2. I mean, you can split it into 2, right? One is smaller or equals to 30, let's say. The other is larger than 30. That is because if we use the information gain as a criteria, splitting the data according to age into 3 partitions is always better than splitting them into 2 partitions. Because when you split them into 2 partitions, for the partition of larger than 30, you can split them into another 2. And this 3, and you will get, you will have a smaller entropy. Okay? So that's why in ID3, when you do the partition, when you split it, you always split the data as into as many partitions as you can. This is important because you will see later another algorithm will construct a binary tree always, while ID3 does not hold this. Okay, let's try to do some computation. Okay, let's say class P for positive means the bias computer equals to yes, and N for negative means bias computer equals to no. And we compute the entropy of age. So for the whole data set D, we have labels equals to yes. We have nine samples, which is here, and labels equal and class N we have 5 samples. So the information of D, or say the entropy of D, is 0.94. You simply use the formula here. Okay, then we want to compute the information gain after we do the partition on age. So for age, we have 3 different attribute values, which is smaller or equals to 30. Then we have 2 positive samples and 3 negative samples. Between 31 and 40, we have 4 positive samples and 0 negative samples. And larger than 40, we have 3 positive and 2 negative. So for each of them, we can compute its entropy, which is here, here, and here. Since we are doing the expectation, don't forget to multiply the portion here. Okay, so if you do the math, you will get this value. And the information gain would be the difference between the expected entropy before and after the partition. And as I said, it always larger than 0. And since it is the entropy, the difference of the entropy, this one is always smaller than 1. So actually, this number always lie between 0 and, sorry. Between 0 and 1, okay? And then you can calculate the information gain for other attributes. And then you will choose the largest information gain, because larger information gain means you will have lower entropy after the partition, okay? That's why we will choose age as the first attribute we're going to use to split to split the data set. Okay. So what is the extreme case? Let's not talk about what is the worst case, just the extreme case. The extreme case would be if, just think if there is an attribute, for example, name or student ID, then for each and every sample, the value of the attribute is distinct, which means if you partition on this attribute, what is the information gain? After the partition, each partition only have one sample, which means after the partition, each partition, the entropy is 0, right? So the information gain is exactly the entropy before the partition, right? Okay, and you can think why it is also the worst case, but we will leave it later. Okay. Okay, let's see. We have already talked about the information gain, which is used in ID3 algorithm. And now let's look at another partition criteria or selection criteria called Gini index. And this one is used in another algorithm named cut. Okay, so in Gini index, all the attributes are assumed to be continuous valued. And assume that there exist several possible split values for each attribute. Of course, for categorical attributes, we can modify it to do the similar thing, which will be shown later. And by using Gini index, we will do a binary split, which means the decision tree would be a binary tree. And we will see why. Okay, let's forget the formulas and here. Let's first talk about the intuition of Gini index. So Gini index is basically how often or how likely you're going to make mistakes. Just remember this, you can do the derivation by yourself. Be more specific. So let's say we randomly choose an element from the set, and we assign it a label. How do we assign a label to it? We assign the label based on the distribution over the whole set. Okay, then of course we can be right, we can be wrong. Then Gini index is to measure the probability that we make the wrong label when we do such thing. Okay. Yeah. So let's look at this part first, because this part is just the simplification of the later one. Okay? So what does this sigma of pj times 1 minus pj mean? As I said, we randomly choose an element from the set. So pj, again, is the same as we defined for information gain. Okay? So this pj is the probability that we randomly chose an element of a specific label. And if we label it according to the distribution of the label of the whole data set, we have probability of pj to assign it the right label, and the probability of 1 minus pj to assign it the incorrect label. So which is this part? Sorry. So we multiply pj and 1 minus pj, we will get how often we incorrectly label such a random chosen element. Okay, and by simplify it, we could get this part. This is just for you to compute the value. And now we consider if we split a data set T into two subsets, T1 and T2, with the size N1 and N2, then the Gini index of after this splitting, similar as what we do when we compute the information gain, we also calculate the expectation. That's why we calculate the Gini index of T1, and we multiply the portion of T1 over T, which is N1 over N. And we do the same thing for T2. This brings us the expectation of Gini index after the splitting. And since the Gini index is to evaluate how often we made a mistake, so we want the Gini index to be as small as possible. That's why we take the smallest Gini index after the split, and we take it as the as the attribute and the attribute value for us to split the node. And just be aware that we need to enumerate all the possible splitting points for each attribute. So let's try it on some cases. So first one is numerical attributes. For example, age here. So for age, we have 20, 25, 30, and 40. So we would have all different kind of splitting values. Like if we take 22.5, then we split the data into these two partitions. And for the first partition, there's one yes and two no. And for the rest, there are 6 yes and 1 no. And similarly for the split value of 27.5. And you can do the rest where the third splitting value should be 35 in this data set. Then we can compute the Gini index of S, which is before the splitting. And you can compute the Gini index after the splitting. Okay, for example, the Gini index of 1, 2. Here, 1, 2 means 1 of yes and 2 of no. So in this case, Pi equals to 1 over 3. Sorry, P1 equals to 1 over 3 and P2 equals to 2 over 3. So what you do is 1 minus 1 over 3 to the power of 2 and minus 2 over 3 to the power of 2. And so on and so forth. You would get the Gini index for different split values. And you will choose the smallest one. So for categorical attributes, it's a little bit different. So for example, here car, you have three distinct values, which is M, T, and S. Then we do this, because we do the binary split, we can split them into M and not M, or T and not T, and S and not S. So always remember, when you do the Gini index, you need to consider all the possible splits. Okay, so this is S and not S, T and not T, and M and not M. And you will get this table, and you can compute the Gini index. And this one's smallest, so if you do the splitting, you should split on T and not T. So okay, so for For ID3, as I have already mentioned before, after the split, after split on attribute A, let's say, you will never split on attribute A again in the subtrees. Okay, because there's no need to do such things. But in CART, which uses the Gini index, you can think in the previous example, let's say we split on this car by T and not T. So for the partition which contains both M and S for the attribute car, you may do the splitting on car again. It depends on when you compute the Gini index, maybe this attribute, the Gini index is still the smallest, so you choose it again. Okay, which means in CART, if you still remember, it's a long time ago. Yeah, here. This condition is kind of different from ID3. Okay, the algorithm we were talking in this slide is for ID3. But for CART, you need to carefully define what is remaining attributes. Okay. And also, since CART is, you use Gini index, you always do the binary split. So CART would be a binary tree. So these are the two major differences of CART and ID3. One is the criteria of selecting the attribute to do the partition, and the other is this makes them one is the binary tree, one is not a binary tree, and the other is CART can have same attribute multiple times, but with different splitting criteria on a path from root to leaf, while ID3 won't have such kind of same attribute showing multiple times on a path. Okay. So overfitting. Overfitting is a very annoying and yet important issue that you will always have to deal with when you use a classifier or when you learn some make a machine learning project. I think we will give a little bit more examples later. But for decision tree, more specifically, it can be overfit if there is too many branches. Okay, then some branches may reflect anomalies due to noise or outliers. And another thing is that for unseen samples, the accuracy would be very low. And if you still remember, when I talked about the extreme case of information gain in ID3, when you use name or student ID as the attribute to do the partition, you can image the decision tree you've got. Although the information gain is maximal, when you see a new name or a new student ID, you have nowhere to go. So this is kind of overfitting. And for decision tree, two approaches to avoid overfitting is So basically, the idea is to make the tree or to make the model simpler. Okay, so you can either pruning the tree after you construct it, or you pruning the tree during the construction. So if you do it during the construction, it's pre-pruning. And if you do it after the construction, it's post-pruning. So for pre-pruning, you need to decide whether you split or not split a node based on the threshold to help you to justify whether it will result in the goodness measure. And the problem is that it is difficult to choose such an appropriate threshold. And the post-pruning, you remove some branches from a fully grown tree. Then you need to decide when to prune and which subtree need to be pruned. And we will talk about this later. Let's see a little bit more examples of overfitting. So in this example, these are the animals that we have as the sample, or as the training data. Okay, and what we are going to do is we're trying to predict if it is mammal or not. And based on these samples we have, we have such a decision tree which has no training error. So training error is 0. But because of this little thing, you know platypus, right? So it's very unique mammal. And because of it is the only mammal in the training data, you have a very overfitting decision tree. Just think of if I ask you dog, if dog is a mammal, so dog, the body temperature is warm, and dog does not hibernate, so dog is not a mammal, or human being, or kangaroo. Okay? So sometimes a smaller model, although there is some training error, but it's more generalized. It can give a more reasonable and better testing performance. Although in this case, the platypus, I think, does not fall here. So the training error is 20%, because there is one error in the training data set. But with this model, we can predict most of the animals in the Earth. So here is a figure about overfitting and underfitting with different number of nodes in the decision tree. As you can see, when the node is very small, both the training error and the testing error are high. Okay, high means not good. All right, which means which indicates underfitting, because your model is too simple. And overfitting, when you have a large number of nodes, your tree is complex, the training error will go decreasing. But that does not happen for the testing error. And the testing error even will increase. And the difference would be larger and larger that actually indicates there is an overfitting. So when you do your project, when you do your lab, you can see this phenomenon a lot of times. You need to be very careful about this overfitting thing. Because there's always students ask, like, I've got very 99% training accuracy, why I've got such a low score? That is because your model is overfitting. That's almost the first answer that I could give. Another example, a very cute cat, but it's overfitting. And this one is for the regression and it's for linear regression and classification examples. I think this would be this would be mentioned again in next week's lecture. Okay, so let's go back to the overfitting on decision tree and how do we prevent overfitting. So for decision tree pruning method, we can use a separate validation set. I think this has been mentioned in last week's lecture. So we use the validation set to estimate the generalization or the test errors. Or we can use all the data for training, but we apply a statistic test to estimate whether expanding or pruning a node, whether it would improve the entire distribution or not. And or we can use minimal description length principle to hunting growth of the tree when the encoding is minimized. We will give details about this specific post-pruning algorithm called pessimistic post-pruning. So the intuition or the idea of the algorithm is try to prevent the model from being too large. Okay, so how it does, how it do that is to add a penalty with regard to the size of the model. So if we observe on the training data, for each leaf node, the small t, we define E of t, which is the arrow on this leaf node. And for the whole decision tree, we define the arrow is the sum of all the arrows on each and every leaf node. Okay. Then we define the generalization arrows, where we use the pessimistic estimate. So for each leaf, we add a 0.5 as the penalty. We for the whole tree, we will add 0.5 times n, where n is the number of leaf nodes in T, as the penalty of the model. So you can think when the model have more leaf nodes, it will have a larger penalty. And let's think of a simple subtree where there is a node and some leaves. If we do not have these leaves, if we only have this node, then the generalization arrow would be the arrow of t plus 0.5 because there is no leaf nodes here. Then we do the post pruning from bottom to up. For each internal node, if the generalization arrow reduces after we do the pruning, means yeah, we'll see an example later. Then we replace the subtree by a leaf node. And after we replace, it's like we're pruning the subtree. Okay, so after we pruning the subtree, we use majority voting to decide the class label. For example, here, we want to decide if we should do the splitting on A or not. So if we do not do the splitting, on A there are 20 yes and 10 no, so the class label would be yes, which means there are 10 arrows. And the pessimistic arrow, we just need to plus 0.5 here if we do not do the splitting. Okay. After we do the splitting, this is what we have. And our class label would be yes here, no here, yes and yes. So the arrows is 4, 3, 1, and 1. So the total arrows is 9. It's 9 here. And the pessimistic arrow would be 9 plus 0.5 times 4. 4 is number of children of this node. Then the pessimistic arrow is 11, which is larger than the pessimistic arrow of the node A. Which means if we split on A, we will get a larger pessimistic arrow, which means the penalty is too large. That's why we need prune the subtree at A. So we will leave A as a leaf node. And we will give the label of A as yes. So in order to further enhance the basic decision tree algorithm, there are several things that we can do in real applications. One is we need to deal with continuous valued attributes. Okay, basically we just do the we just discretized these attributes. Or we can use some specialized decision tree learning algorithms. Another thing is we need to handle missing attribute values. One way to do it is to assign the most common value of the attribute. You know, in real application, it is very common that sometimes you do not have the attribute value for some records. I remember last year I was designing the labs. I used a data set from the weather record in Sydney, and sometimes we missing some attribute values. And another thing is, another way is to assign the probability to each of the possible values. The third thing is the attribute construction. Okay, think of sometimes the attribute you have does not represent or does not very well correlated to your label. For example, when I looking at the weather record in Sydney, I want to see if it is cloudy or not. So cloudy or not is the label, or it's the thing that we're going to predict. So whether it is cloud, we have attributes like the temperature in the morning and the temperature in the afternoon, but or the temperature in the evening. And these attributes does not directly correlated to whether it is cloudy or not. However, if you do the minus, if you get the difference between the temperature in the morning and evening, you would see that it's actually relevant to whether it is cloudy or not. So that requires you to have some domain knowledge of the training data or of the data, and you carefully design or add a new attribute. It will help you to get a better performance of the decision tree. Okay. So this slide is trying to answer why we need decision tree in data mining. So basically, we need to do classification, as it is a classical problem in statistics and machine learning. And we want to classify data sets. We want to classify a large data sets. Okay? A large means you may have a large number of examples or samples, and you have a large number of attributes. And we want to do it in a reasonable time. So decision tree is relatively faster compared to other classification models. And it is simple and easy to understand, which is quite important for data mining, because for some of the models, it's kind of hard to understand. For example, neural network. But for decision tree, you can easily extract the rules, and you can use the rules to write some SQL queries. Then you can get the data. Okay, and the accuracy or the performance of the decision tree classifier is comparable with other methods. So that's why we still the decision tree and its variant still widely used, even in the current research and applications. Okay, let's have a 10 minutes break, and after we come back, we can talk about Bayesian classifiers. 加的是这个 arrow， 大的是你的这个你选择的这个 label。比如这个是8，这个是4，对吧？那么对于这个 node 的话，你选的这个 label 就会是 yes， 对吧？这个时候你选了 yes， 那么这8个是对的，这4个不就错了？
这4个不是 no 啊，我知道了，哦，我懂了。I have some questions about the pessimistic distribution.
Okay.
Do you know why is it 3.5? Oh, it's just a number.
Just a number.
Like, does it have any like proof or something, or like, or just like rule of thumb or something like that?
Not really. I mean, in machine learning, so the original algorithm, I looked at the textbook, and the original algorithm just gives 0.5.
So there's no explanations. Like,
Yeah.
everyone's just using it.
You can think of like if you increase this number, so the penalty of the model size is greater. Yeah. If you reduce the number,
So it's flexible.
Small, yeah. But it's like using 0.5 is the most common way. Everyone thinks this number is fine.
Oh, okay. Another quick question is like, I don't get why is it 9? Because when I count the number here, it's 10. So I
No,
don't get.
it's not class equals no. The thing is here, right? For this node, the label you will assign to it is no,
Yeah.
which means the arrow is 3.
Oh, I get it now. Okay. So this
Okay.
is.
Yeah, because this is yes. So if we change this to A and B, it may be more clear.
But what about now? Where it comes from?
Okay, so for this point,
Yeah.
which label would you assign for A1?
Yes.
Yes.
Yes, right?
Yeah.
So the arrow is
4.
4. So what about this node?
Arrow is 3.
Yeah, arrow is 3. This one's 1 and 1.
So we add them up.
Add them up, it's 9.
Oh, okay. Right, thanks.
So I was looking on how to calculate Gini index, right?
Okay.
So you can make calculation based on say like looking at attribute 1 and I calculate attribute 1 and maybe class A, and then I calculate the second one to compare it to second one and say attribute 1 but attribute 2 but class is like class B, but like say attribute 2 doesn't just have a discrete number of classes. Attribute 2 is a continuous number of,
Okay.
it's what makes you decide on which way to split.
Yeah. Actually, the first thing you need to do is to discretize the attribute 2,
Okay.
although it is continuous.
Yeah.
So you still remember binning.
Yes.
Binning is a way to do that.
Oh, okay.
Okay. So you make it discrete, then you can insert some kind of the splitting points.
Yeah.
Okay. Then you try to get the smallest. So So you cannot directly do it on continuous value.
Okay. And say, for example, after I've done binning, does choosing any of the bin has the same effect, or do I just choose a random one and continue to experiment?
Sorry, I don't get
So, like, say after I've discretized everything, and I still compare to attribute one, class A, but when I choose from a bin in attribute 2, do I just choose a random bin, or do I choose, or
No,
all the
you-
bins are exactly the same, or
No, not all.
no, I'm not saying exactly the same as they contain the same set of values or anything. I'm saying
First
do they
of-
have the same worth?
Yeah. First of all, I don't quite understand what do you mean by attribute 1 class A and attribute 2 class B? Because there's nothing to do.
Oh, sorry, not class. The type of values.
Oh, okay,
Available.
okay. So you actually try all the possible ways of partitioning, or all the possible cutting points, and each of them will bring you different Gini index.
Oh, okay.
For example, let's say you have 2 attributes. Okay.
Yeah.
You try all the possible cutting on attribute A, and then you do the same thing for attribute 2. Attribute 2. Let's say you have 3 cutting points for attribute A and 3
So
for
the
2.
number of cutting will be the number
6.
of the first one times the second one. Number of
No,
cuts in the first
plus.
one.
Because
Plus?
each time you do the splitting on one attribute.
Yeah, but no, I'm saying the number of total cuts you have to try is
6 is plus, because you you do the partition
Yeah.
based on one cutting point on one attribute. So for A you've got 3.
yeah,
Let's say for attribute 1 you've got 3.
Yeah.
For attribute 2 you've got, let's say, 2.
yeah,
Okay. So all you have is 5 different cutting points.
yeah.
Okay. Then you will get 5 Gini index values.
Yeah.
You've got the minimum one. It could
Okay.
be on a splitting on on attribute 1 or a splitting on attribute 2.
Oh, okay.
But
I
you
get
just
what I
take
mean now. I get what you
one
mean
of
now. And but for this one, would it be more efficient than just calculating entropy? Like, what's the efficiency between calculating this Gini index and just doing information gain on entropy? Like, is there any advantage in any of them? Like, both of them seems like a really computationally exhaustive.
Yeah, actually, they have different perspectives or different focus. But let me see. I'm a little bit nervous because I may not remember this, but I did do some research on this. It's not right here. I can't remember clearly, but if you access to the textbook, I think it did mention somewhere. So information gain has a serious problem or drawback. That's why they invite Gini index later.
Okay. But I was reading off somewhere as well. It says when you do calculate Gini index, you don't just use Gini index anyway, because, well, at least what I read up was after you can pick the minimum Gini index, you still need to do a information gain calculation.
At least this is not in the card already.
Okay. It's a custom one then. Okay. So if it's just cut, that means you just pick the minimum Gini
Yeah,
index.
yeah.
Okay. Alright, I get it. Thanks.
Okay, let's go back to the. Yeah. Let's continue. So in this example, some of you may getting confused. So let's try to not use yes and no as the class label. Let's simply use A and B, which hopefully would be more helpful. Okay? So after you do the splitting, you need to select a label for each and every node. And you select them by majority voting. So for A1, you would select A as the label. And for A2, you would select B. And A for A3, and A for A4. Okay? Then you calculate the error. Then the error for A1 is the number of elements or samples that the class label is not A, which is B. So it's 4 here. And for A2, because the label you assign to A2 is B, so the error is the number of elements whose label is not B, which is A. So it's 3 here, and so on and so forth. That's why you add the circled numbers together, you've got 9 here. Okay. Okay, so let's start the Bayesian classifiers. So the first question is why we need a Bayesian classifier. So decision tree classifier is like gives you a set of rules, but the rules are quite strictly. It's like I still remember when I was a child, when I watched the movie, the most frequent question that I would ask my parents would be, is this guy a good guy or a bad guy? Right? When I was a child, I always do this. And after questioning this again and again, I would have a classifier in my mind. And at the beginning, the classifier is usually a decision tree. It's like, if you saw this one killed someone, he's a bad guy. If you saw this one help someone, he's a good guy. Okay? Then one day my world is collapsing because I saw James Bond. Okay? He killed people, but my father told me that this one is a hero. He's a good guy. I said, what? Okay. And then I reviewed the classifier in my mind. This time I decided to use Bayesian classifier. So what Bayesian classifier did is like, okay, if you saw this one killed someone, well, his probability to be a bad guy is increasing a little bit. And if you see this guy help someone, the probability of his being a bad guy is decreasing. Okay? So eventually, all I can tell is, well, this guy is more like a bad guy than a good guy. But in decision tree, eventually you will have this one is a good guy, or this one is a bad guy. Okay, that's why we need a Bayesian classifier, because it can gives you a probabilistic prediction. And another thing is, think of the same example. Okay, it's like after I've built the decision tree, one day I saw in the movie this person steal from people. But I never saw a person steal from people before. Then after I realized this is a bad guy, I need to rebuild the decision tree in my mind. But if I use a Bayesian classifier, it just increases the probability of this guy being a bad guy, it does not affect what I have already known before. And you will see why later. Okay? And then we say, even when Bayesian methods are computationally intractable, they can provide a standard of optimal decision making against which other methods can be measured. So it's kind of a standard. So before we go into the classification algorithm, let's review the Bayesian theorem first. So let X be the data sample whose class label is unknown. So this X, in the real application, or when we really deal with a class file, this X is usually a vector, a feature vector. For example, if we use, I don't know if, yeah, okay. For example, this X1, it has 4 features, which is age, income, student, and credit rating. Okay. And let H be a hypothesis that X belongs to class C. In the previous example, the class C is a biased computer or not. Okay. Then for a classification problem, we need to determine probability of H given X. So this is the probability that the hypothesis H holds given that we have observed the data sample X. Okay, you always need to remember, this is your goal. You observed X, you predict or you calculate the probability of H. Okay? And the probability of H, there's no given X here, is the prior probability of hypothesis H. Okay, it's like the initial probability before we observed anything. Okay, it is like if I ask you, let's say A, I ask you A is a male or female, you can only give a 50% guess. 50% probability it's a male, and another 50% it's a female. And the probability of X is the probability that the sample data is observed. And the probability of X given H is the probability of observing the sample X given the hypothesis H holds. So the Bayesian theorem gives us the relationship between these 4 probabilities. I think the formula you have already known it before. So we call this PH given X the posterior probability. This PX given H the likelihood. The probability of H is prior and the probability of X is evidence. Since the X is fixed, so we don't really care about probability of X. That's why in Bayesian classification, the final number you've got is actually proportional to the probability of H given X. It's not the real probability, okay, because we don't really calculate X here, because X is the same for different H. Then, what we want to get is we want to get the H, which is the H from all the possible hypotheses, such that the probability of H given X is maximum. And this one is equals to to get the argmax of h of the probability of x given h times probability of h. This is because directly compute the probability of h given x is hard. So we compute the probability of x given h and the probability of h. And later you will see this one is easy to compute as well. So all our efforts is to compute the probability of x given h. We still use this example, and let's assume the data sample is we have the features, the feature values where age small o equals to 30, income is medium, student is yes, and credit rating is fair. Then the first thing is, what is the number of probability of h? Here we do a MLE. The intuition of MLE is quite simple. It's like, let's say, I've got these statistics just before I come to the class. You know the goalkeeper Buffon? He, according to the website that I visited, he saved 31 penalties out of 100 in his past career. So what is the probability that he will save the next penalty? It would be 31%, right? So quite intuitive. That is the MLE. And all this part is the mathematic derivation. How do we get this number? So let P be the probability that the class is C1. And let's consider a training example X and its label. Okay, so the label Y could be C1 or could be not C1. Let's consider the binary case. So the likelihood of X is P to the power of Y times 1 minus P to the power of 1 minus Y. Okay, let's say if Y equals to C1, we assign the value to be 1. And if not C1, we assign the value of Y to be 0. Now this likelihood would be, if it is C1, if Y equals to 1, then it is P times 1 minus P to the power of 0, which is P. And if it is not C1, then it is 1 minus P. Okay, so it just gives the likelihood, and trying to write this kind of the results into one formula, and then the data likelihood, which is the likelihood over all the data, would be the multiplication of all the x. Multiplication of the likelihood of all the x. If we take the log, where the log data likelihood would be the summation of y log p plus 1 minus y log 1 minus p. We are trying to do the maximum likelihood estimation. That's why in order to maximize this log data likelihood, we do the partial differential on p. And we would have P equals to sigma y divided by n, where this sigma I, this sigma y is actually the number of samples that have label of C1. That's why you would have probability C1 is 9/14. It is because in this example, C1 is yes and the C2 is no, as the hypothesis listed here. So there is 9 yes in the whole data set and 5 no. That's why you've got probability of C1 is 9/14 and C2 is 5/14. So the estimation of probability of H is easy. But to do the MLE for probability of X given H is not that simple. If we directly do it without any assumptions, basically we would need to see all the possible X. Even we assume that the distinct value for each attribute is 2. We would need 2 to the power of D training examples, where D is the number of features. That's why we actually made a very strong and important assumption to make the whole problem much easier. So we assume that the attributes are conditionally independent. As such, the probability of X given C1 equals to the multiplication of probability of Xk given C1, where Xk Xk is the value of X on attribute K. So there is n attribute. Okay. So for each probability of Xk given C1, you can think if we do the MLE, it would be the number of samples in CI or have the label CI where the attribute of AK equals to XK divided by the total number of samples with label CI. For example, let's say the probability of age equals to small o equals to 30 given C1 would be C1 is yes. So yes is great here. So it's 2 because there are only 2 samples which C1 equals to yes and the age equals to smaller than or equals to 30 is the total number is 2 divided by the total number of samples with the class labeled C1, which is 9. Okay, so you simply do the counting and you can get the number. So before we need to have or need to calculate probability of X given CI. And now we only need to calculate the probability of Xk given CI and do it for all n attributes, and we would have the value of this one. Okay, it seems that here I need to do the calculation. Okay, remember CI is yes and C2 is no. So for this data sample X, we first compute age equals to given C1. Let's find all the attribute, all the samples with attribute age is smaller or equals to 30. Then this one, as we've done before, is 2/9. And C2 is 3/123/5. And similarly, you can do income is medium given C1. So you've got all the medium. So it's 2/9. And given C2, the number should be for us. Sorry, this is 4/9 and this is 2/5. Yeah, this is 3/9, 2/5. Oh no. Okay. And you can do it for the rest. Multiplying them together, like here, you would get the probability of X given CI. But don't forget to multiply the probability of CI, because eventually what you want is the probability of CI given X. Okay? Because you want probability of CI given X. And the two numbers you've got here, the larger number represents the larger probability. But it's not exactly, as I said, it is not exactly the probability of CI given X. But the ratio of these two, or which one is larger between among these two, did give you the idea of which CI is more likely to be the label. Okay, so everything looks simple and and crystal now, except there is a devil hiding in the details. Let's go back to the example when I watched the movie and try to figure out if he's a good guy or bad guy. So I've built a Bayesian classifier, and the classifier works very well. And one day I saw the guy in the movie punched another guy. And well, my classifier collapsed again because I never saw a man punched another guy in the movie. So in my classifier, let me see, given, given he's a good guy, he punched someone, the probability, according to MLE, the probability is 0. Given he's a bad guy, he punched someone, the probability is also 0. And remember, we need to multiply all the probabilities, which makes us get the 0 in the end. So, which means if this one punched another guy, both he's a good guy and the bad guy, given he punched someone, and he did a lot of other things. He can punch someone and help people, or punch someone and kill people. The probability is always 0. Means I cannot make any decision. Okay? So this makes the model very not robust. So the solution is also easier. Yeah, it's also easy and simple. We simply assign a small probability to such case. Because all we want to do is we don't want any probability to be 0. Because anything times 0, you got a 0. Okay? So this add-one smoothing is trying to assign a small probability for this kind of unseen probabilities. But you still need to do one more thing. You need to make sure that the total probability still equals to 1. Let me see, this is not, okay. So previously, when we compute xi equals to vj given ck, we simply do the counting. Okay, we count xi equals to vj and the class label is ck divided by the total number of ck. And now we add 1. We add 1 here, and add 1 here is called add-one smoothing. It is because when this, you can think of if the count here is 0, you still got 1 divided by something. But previously you would get, let's see if this is 0. Previously you will get a 0. Okay. So the next thing is, in order to make sure the total probability still equals to 1, we need to decide the value of b. So the value of b would be the number of values that xi can take, or let's say the number of distinct values for x of a specific attribute. Let's say the example which could be more straightforward. Let's say we modify the table. Now there's no instance of age smaller or equals to 30 in the no class. Okay. Then when we want to predict the class of this x, we need to compute the probability of age smaller than or equals to 30 given C2. C2 is no. Previously, we would get 0. Now we would have 0 plus 1 divided by C2 is 5, but we need 2 plus b. So what is the number of B? The number of B is the distinct value of this attribute. So for attribute age, the number of B should be 3. And for, let's say for income equals to medium, given C2, the previous value would be 2 over 5. Note that even for those values are not 0, we still do the add 1 smoothing, okay? And the distinct value of income is also 3, so we add 3 here. More examples of calculation can be found here. As you can see, the B equals to 3 and 3. Here 2 because there is only yes and no. 2 is fair, 2 for fair and excellent. That's why here is plus 2 and here is plus 3, plus 2. And then you can calculate the probability of X given CI, where you multiply all the numbers you've got above, and don't forget to multiply probability of CI. When you calculate probability of CI, there's no need to do add 1 smoothing, okay? Because you will always see 2 different labels, otherwise there's no need to do classification. And you can see the probabilities of the different values of a given attribute given a fixed class label. The summation is always 1, no matter you do or do not do the smoothing. But just remember, doing smoothing is not optional. Doing smoothing is not optional. You should always do smoothing, no matter it asks you to do it or not. Because if you do not do the smoothing, you cannot handle the 0 case. Another thing is, actually you can do add 2 smoothing, or add 3 smoothing, or more generally add alpha smoothing, but without specifically giving you the number of alpha. We usually do add 1 smoothing. Where this alpha is just trying to adjust the weight of the unseen unseen attribute values. Okay. The next thing is, if you noticed that what we were doing before is trying to handle the categorical values, but how to handle numeric values. There are two methods. So the essential idea is all we need to do is to model or to estimate this probability of xi given ck. So the first method is we assume that it follows a certain distribution. And usually we use Gaussian. Then we're trying to estimate sigma and mu. Then we have then we can write down the distribution. then we can predict this number. The other way is to use binning, where it has already been covered in last week's lecture, right? You use binning to discretize the feature values. Then you make them from continuous values to discrete values. Then you can do the rest things as you have already familiar before. Okay. Let's have a 10 minutes break, and I will finish the rest part.
For that PowerPoint,
Yeah.
53.
53.
So here, when you multiple probability of CI, why you don't need any smooths?
So the probability of CI is you estimate this value based on the whole data set. So the whole data set, if the whole data set, here you won't face a zero problem.
Yes.
Because if there's a zero, let's consider the binary case. So if one is zero, then the other is one.
Yes.
So you don't need to do the classification. Because everything you can tell from the training set it is always SAC1.
So for the CI, it's always bigger than zero. So that's why you add smooths.
Yeah.
Okay, thank you.
You only add smooth for each and every component here. So to do it here, but no need to do it for CI. Yeah.
But here you still need 80 smooths.
Where? This one?
Yes, this one.
Yeah, this one is smooth because this one is a multiplication of these four, and
Yes.
each of them has already done smoothing. So you don't do the smoothing again. Yeah. Because this is a simple multiplication. So that's the problem.
Yeah, thank you.
我再问一个问题，不过是关于 Lab 3，可以问吗？
可以啊。
就是假设 spam 里面有个 U 是2，然后总共有50个 word，总共的出现次数包括 U 是60。根据你刚才说，就是60加50分之3。
我们这个一会儿会讲到的。
好，因为我就纠结了这个问题。
OK， 因为对，马上后面会，因为 Lab 3讲multinomial那个 FDS， 我们不是还没说到吗？
不过我们学了941，其他有讲。
I see。
但是我用那个算了也不是不对。
因为后面那个反正会把那个公式给出来。好，对。 Okay, let's continue. So now let's study a real example of application that knife-based has been widely used, which is text classification. We will first introduce some applications, and we will introduce two different, slightly different classification methods or models based on two different language models. So the document classification problem is like giving you a query document here. It has some words, and you're trying to categorize it into different classes. For example, in this example, there are you need to decide whether this text is about machine learning or planning or semantics and so on and so forth. And the problem is you can think of why you cannot use or simply use decision tree in such kind of problem, for example. And it's just like how human beings do the task. I mean, it's more like you saw a word and you think, wow, for example, you saw the intelligence, you think, well, it may be related to AI, and you saw language, you think it may be related to programming languages, and so on and so forth. So it's more like, intuitively, it's more like a knife-based model. And so these labels we're talking about can be topics, like finance or sports, can be genres, can be opinion, or language identification, or spam or not spam, like what you are going to deal with in Lab 3. So remember, when we trying to use knife-based, all we need to do is the ultimate goal is to predict class given text. But since class given text equals to probability of text given class times probability of class, and the probability of class is easy to estimate. So all we need to focus on is to model probability of text given class. And there are two methods. The first one is based on a statistic language model, which turns out to be the bag of words model. If we use unigrams, we will introduce it later. And this one's called multinomial knife-based. And the other model is to view the text as a set of tokens. Again, we will give the details later. So this model falls into a Bernoulli knife-based model. So let's first start from multinomial knife-based. So we want to model the probability of A, B, C, D, such kind of text. And according to the probability series, this probability equals to probability of A times probability of B given A, and probability of C given AB, and so on and so forth. But we can simplify this model by using the unigram model, also called zeros order Markov model, where we assume that probability of D given ABC equals probability of D. Means the probability of D has nothing to do with ABC, or has nothing to do with the word before it or after it. It only depends on itself. And so does probability C. So C given AB is equals to probability of C, and so on and so forth. We won't use this bigram language model, but it is good to know that it's also called first-order Markov model, where we assume that the probability of D given ABC equals to probability of D given C, which means the probability of a token is only depends on its previous token. Okay, and this model I think it's used by Google. And the same holds with class conditional probabilities. Like if we want to compute the probability of A, B, C, D given C, if we use the unigram model, it would be probability of A given C multiply probability of B given C. This is the big C for the class, and the small c given C, and the D given C. Then the probability of each class is done as a class-specific unigram language model, where when we compute, let's say, here's an example of a text with 4 tokens. So the probability of Cj given this W1 to W4 is proportional to probability of Cj, where we can easily estimate, times the probability of W1, W2 to W4 given Cj. And this part equals to this part, because we use the unigram model. Each token here only depends on itself. So it can be written as a probability of Wi given Cj and multiply all the 4 i's here. And if, let's say, there are duplicate Wi in this text, then it falls to the bag of words model. For example, let's say W1 equals to W2. So it would be, you can think of like you multiply W1 given Cj twice, because each token is only conditioned by itself, and if the 2 tokens are identical, you can merge them into one. Basically, these 2 are the same. So in this case, for each text, we can write a vector like the xi and theta I, where xi is the words in the vocabulary. For example, if we use to be or not to be as an example, the distinct words in the vocabulary would be to, be, or, and not. So the corresponding theta I is the number of times that this token or this word appears in the text, which would be for to would be 2. B is 2, and 1 for all and 1 for not. So you've got xi and theta I. Then you can compute this one. And for for the probability of xi given Cj, you simply do the counting, just like what we did before. So in the learning part, we first extract the vocabulary from the training corpus, and we calculate or estimate probability of CI and probability of xk given, probability of Cj and probability of xk given Cj. Well, this probability of Cj is the number of documents which the target class is Cj divided by the total number of documents. And the probability of xk given Cj here, this is the formula, where vocabulary is what we extract at first. And this nk is the number of occurrences of xk in text j. This text j, you can think it is a mega document which contains all the documents in the data set. Sorry, all the documents in docs j, because we have a Cj here. So if there are only two classes, you need to construct two texts. Text 1 with class label C1 and text 2 with class labeled C2. And this alpha is for smoothing. Okay, if we use add one smooth, then alpha equals to 1. If we use other values, you need to change the alpha. And then you can try to figure out what this n is. Just remember, you need to make sure the total probability equals to 1. So it is not hard to figure out what is n. And to do the classifying, firstly, you've got the positions, where the positions is for a given document, you get all the word positions in current document which contain tokens found in the vocabulary. And you simply for each position, so say for each word, you compute the probability of xi given Cj. And you multiply them together. You multiply probability of Cj. You've got this part, and you find the Cj which can gives you the maximum value of this one. So the training time complexity would be contains two parts. Sorry, the LD is the average length of a document in D, where D is the corpus. So this D times LD is when you compute the frequency and get the vocabulary. You can do them in one round. And C is the total number. C is the total number of classes, and V is the vocabulary. So CV is actually when you this cost occurs when you compute the likelihood. And generally, because CV smaller than D times LD, so we usually only need this part. This is because you can think of if we write the inequality in this way, it might be more clear because C is usually a very small number. In real applications, C usually equals to 2. And then you can see your vocabulary size usually much smaller than the right-hand side of the inequality. And for the test, the LT is the length of a test document. So you only need to go through the document C times, each time for a specific class, and do the computation, and you get C different probabilities, and you take the largest one as your final prediction. So there's one problem, is that because we need to, let me see. Yeah, because we need to do a lot of multiplications here, and each probability of xi given cj is smaller than 1. You can think of, if you multiply, because we're doing text classification, these positions could be like hundreds or even thousands. And each of the probability here could be quite small. Even they're close to 1, it doesn't matter, because when you multiply so many numbers smaller than 1 together, you would eventually get a number very close to 0. And when you do it in computer, it may cause a floating point underflow. So in order to solve this problem, we use log instead of directly do the multiplication. So if we apply log on both sides, again here, we do log on both sides of the equation, we would have log of pcj plus sigma of log of p xi given cj. Okay, just like what you saw here. Then you do not need to do the then you won't do the multiplication, but the summation, and you avoid the underflow issue. So far, it's for the multinomial model, and for Bernoulli model, we model the text in a different way, where each text we extract a binary vector. If you still remember before, for each text, the vector is the value of each element could be 0 or 1 or 2, or even larger, depends on how many times it appears in the document. But in Bernoulli model, this number 1 or 0 indicates that whether the token has appeared in the document or not. If it has appeared, then it's a 1. Otherwise, it's a 0. Okay. Then after you get the vector, you can directly apply naive Bayes. The rest thing is simple. So if we compare the two models, there are two things. Yeah, there are two things that we need to aware. One thing is the multinomial model is, so for one feature, each feature corresponds to each word position. And for Bernoulli model, each feature corresponds to a distinct word. So if the word appears multiple times, then the multinomial model will record the number of times that this word appears, while the Bernoulli model will only record a 1. So it will ignore the the multiple times that a word appears. The other thing is they have different assumptions. For multinomial model, it actually assumes that the word in one position tells us nothing about the words in other positions. And the second assumption is that the word appearance does not depend on positions. So you can think to be or not to be, not to be or to be, BB to, not all, they're all the same. Okay. And in Bernoulli models, the assumption is that appearance of one word in the documents tells us nothing about chances that another word appears. That's why for Bernoulli model, the estimate probability of xw equals to t given Cj is the fraction of documents of topic Cj in which word w appears, while the multinomial model is the fraction of times in which word w appears across all documents of topic Cj. And multinomial model is almost always more effective in text applications. There's a paper did some experiment, and this is one figure from the paper. Actually, this one is one of the out of the 4 different data sets. This one is the most close of the give the most close performance of the 2 different models. The red line is multinomial model, and the blue one is Bernoulli model. So basically, Bernoulli model only outperforms multinomial model when the vocabulary size is small. But when the vocabulary size is large, and eventually multinomial model would beat Bernoulli model. So in general, the feature selection is necessary for Bernoulli model. This is because feature selection is like you cannot. So here, each feature corresponding to each word in the vocabulary. So as you can see, when the vocabulary size grows, the Bernoulli model actually the performance is reducing. That's why you need to do the feature selection in order to keep the performance better. Otherwise, you will suffer from noise or multi-counting. Multi-counting is like we'll see another example later, but let me give you some idea. It's like Hong Kong. These 2 words always appears together, and but in Bernoulli model, you actually count them twice. Then you multiply this probability twice, where you only need to multiply it once, because they are essentially one word, not 2. And how this would affect your model, we have an example later I will show. And this one is to show the, so these are classes. These are classes, and these are tokens. So this numbers is the likelihood of each token given the class. And the listed tokens and the numbers are the highest ones. So you can see this gives us an intuition of how to understand or how to explain the naive Bayes model. For example, for students, if you see resume or advisor or student working staff links, it indicates that this text is highly or is likely to be about students. This is another example showing the advantage of naive Bayes, which is the blue line here, on identifying spam emails. So when we use naive Bayes models, we need to remember that we have made some assumptions, which is the conditional independence between the features. But these assumptions not always hold. In text classification problems, this conditional independence most specifically is positional independence. And let's give a general example. Saying if we have two identical sensors at the same location, then they would always give the same results. And this is what we have. So S1 and S2 are two identical sensors. So now we want to compute probability of S1 given C and S2 given C, but they should always be the same. Let me see. Yeah. Okay. So the probability of Si equals to positive given R is 3 out of 4. This is 1 out of 4. And these two are both 1 over 2. Okay. Then when we want to compute the probability of R given SS, which is the probability of SS times the probability of plus given R times plus given R again. Oh, sorry. Yeah. And and we can do the same calculation for probability of S given plus plus. So the number is 9 over 32 and 1 over 32. So you would make the guess that probability of R given SS is 90% and the other one is 10%. So how would this affect your prediction? Let's say if you have another condition, which is probability of, let's say, S3 equals to plus given R is let's see, 0.1. Then if we add a plus here, what you will get is you would multiply 0.1 here and sorry. .9 here. You get both of them is 0.09. Okay. But the real, the real probability, if we consider only one of S1 and S2, according to here, it would be 0.09. Which actually gives us quite different results. So this slide, I think I've mentioned before. The classification results of naive Bayes are usually fairly accurate, but the number you get is not the actual posterior probability. Okay, and usually the output probability are very close to 0 and 1. So you just focus on the prediction result, but not the numbers. So naive Bayes classifier is easy to implement, and it gets good results in most of the cases. But one of the major disadvantage or major thing that we need to notice that is that the conditional independent assumption. And in reality, this assumption does not always hold. So it will lose the accuracy. And so, yeah, here just a couple of examples where the conditional independence doesn't hold. For example, for a patient, some of the symptoms occurs together, like fever and cough, or some disease happens together, or has very high correlation with each one else. In this case, the we cannot use naive Bayes classifier to model such kind of problems. So instead, we can use logistic regression, which will be introduced next week. Or we can use Bayesian belief networks, which is not covered in this class. Okay, logistic regression is for the next class. Okay, and so unlike decision tree and naive Bayes, there's another kind of learning method called instance-based methods, which store training examples and delay the processing until a new instance must be classified. So it's also called a lazy learning method. And one of the typical approaches is called k-nearest neighbor approach. So the idea is you store all the data points according to their feature vectors in a n-dimensional space, and you can define the matrix of the space to. We usually define the matrix of the space to be a Euclidean distance, and the target function is like what you want to predict. If you want to predict a label, it would be a discrete valued target function. Or if you want to predict a value or a point in the space, it's like it will be a real valued target function. And for the discrete valued target function, the k-nearest neighbor algorithms returns the most common value among the k-training examples nearest to xq. So basically, it first gets the k-nearest neighbors of the query in the data set and do majority voting to get the most common label. You can think of a Voronoi diagram if you know this. It's like a 1NN algorithm. And with this k increase, you can see in this example, the decision boundary becomes more and more smooth. So you can take this k as a smoother. And for the continuous valued target functions, the kn graph get the k-nearest neighbors and get the mean value, or get the center of this k the k-nearest neighbors. And sometimes we can also take the distance into consideration, because we assume that if the distance is larger, means it is dissimilar to the query, then we should assign a smaller weight to such a node. Okay, so basically you get the k-nearest neighbors, and according to their distance to the query, you assign different weights, and you can get a weighted label or a weighted value. Depends on what kind of target functions you are dealing with. And the major problem of using a k-n algorithm is you have to deal with curse of dimensionality. So basically, curse of dimensionality means if the dimensionality is high, then searching the k-nearest neighbors, there's no good way of doing such kind of searching. The best you can do if you want an exact result is to do the linear search. And I just want to give an example of how difficult it is. I've spent my whole PhD life on this specific problem, and all I can get by the end of my PhD is working out an approximate solution. And I still won't call it a failure. Okay, so it's really hard. And also the distance between neighbors could be dominated by irrelevant attributes. So you need to carefully select, or you need to do some axis stretch to eliminate such kind of effects. So the difference between lazy learning algorithms like KN and eager learning algorithms like decision tree and naive Bayes is the lazy method may consider a query instance when deciding how to generalize beyond the training data D, while the eager method cannot, since they have already chosen global approximation when seeing the query. So lazy learning algorithms usually takes less time do the training, but more time do the predicting. And for accuracy, lazy method effectively uses a richer hypothesis space since it uses many local linear functions to form its implicit global approximation to the target function, while the eager learning method must commit to a single hypothesis that covers the entire instance space. Okay, so that's all for today. If you have any questions, you can ask offline, and thank you.太紧张了。没有，还是太紧张了，就是好多地方。反正觉得比想象的还差一点。其实在家也没怎么练，就今天大概就是稍微背了一下。对，因为课以前也上过，然后帮他做过 tutor 什么的，就是大部分东西反正都知道。对，然后就是，但是具体的话就是，可能有些细节的地方，或者是有些例子啊什么的。
下次我问你细节。
好。对，肯定有些地方讲的不清楚。都用过的。做过。
老师叫安南，新
啊，对。哦，对。哦。
我见过他，还听说他到这儿来做生意，他的学生还给我们讲他们打算回家。
行行行。
很高兴你没有回答 tax，因为 forget，你说你走到